Sonic, the heart of your system.
Hi and welcome back to a new video. In today's video we will analyze or test something that is quite unusual, at least nowadays. It's something you have seen probably, I don't know, like 5, 6, 7 years ago. It's something I also showed on my YouTube channel. We developed a cooler in 2014 and showed it on my channel in 2018. It's about TEC cooling. That's a thermal electric cooler. And the way it works is you have those two ceramic plates right here. The white thing is ceramic and in between you have some semiconductor parts. And if you apply a voltage to the TEC, you can introduce a temperature difference between the two plates and therefore basically pump heat through the TEC. And it's a very interesting way of cooling because let's just assume that the hot part or the hot plate will be held at plus 50 degrees Celsius, then your cold plate could be sitting at 0 degrees Celsius, and that would mean very intense temperatures for our CPU. The only downside is that the power consumption of those are absolutely enormous. A big TEC like this one consumes easily like 300 watt, and 300 watt are required for about 150 watt of cooling of the CPU. That is the rough rule of thumb if you just apply a voltage to it and run it all the time. When I designed my own cooler in 2014, I used this controller right here, which is quite beefy. You can tell by the fact that it's still running one of those 5.25 inch bays that it's quite old, it's legacy stuff. It was using a controller and a solid state relay, and the solid state relay was used to switch the TEC on and off. Basically a 2-point controller. Whenever the temperature exceeded a set point, let's say 20 degrees Celsius, then it was switching on the TEC, and once it was reaching, for example, 16 degrees Celsius, then it was switching off the TEC. And that is a very inefficient way of using a TEC, simply because just imagine you're using this thing and then you're cooling the hot side and you're switching the TEC off. Then your hot side is immediately heating up the cold side and also the CPU. And that's why if you're using a 2-point controller, it's basically running all the time. It's a very, very inefficient way, but for me it was fine. I was just constantly running this thing for my overclocking attempts, and in that regard I didn't really care. It was never meant to run 24/7. It was just something I built for myself, never used it myself. It was used in a project we did with PC World, well, the German version of PC World, PC Welt it's called in German. And we used my single cooling block I had in this project. That's why I don't have it here anymore. I just have the single TEC left. Now Intel decided to look into this technology and invest some money and time in it and try to improve the technology. Now we have this EK block. There are different versions out there from different manufacturers. I think even an AIO version, but I guess the custom water cooling version should be by far the best. They also made a dedicated controller, which I gave some feedback on. They asked me about it several weeks ago if I have some feedback on the technology itself and also on the software, which I gave them, and I'm very happy that they asked, because especially in the XTU there was some stuff we could improve, and I hope that this will be better than my solution, because it's using a DC controller, which means that you're not just straight switching off the TEC, but you can also adjust the voltage of the TEC, which is a major advantage. Let's just imagine your 10900K is running an idle and consumes 30 watt. Then your cooling capacity or the cooling heat of this TEC will be way too much. It would just switch off all the time and would be switched on with the 2-point controller. But if you're using a DC controller, then you could just run this at 4 volt instead of 12 volt, for example. Then it's consuming much less power and it will be more efficient, and it's not going to exceed the dew point of the ambient cooling, because that's a big problem of the TECs. If you're running it too low, then you can occur condensation. But let's just analyze or check out what they built and what all those components are. The TEC cooler is made out of 3 metal parts in general. We have this top part right here, which is which Sheik is checking out right now. And the top part is just a cover and also the mounting frame at the same time. And if you check the internals right here, you can see the cooling structure inside. And the cooling structure is inside this copper plate right here. And this copper plate, the middle one, is in contact with the TEC, which is sitting in between. You can see some thermal paste squeezing out in between. And then we have this additional heat spreader, I would call it, on the bottom, mainly because the TEC itself is quite a bit larger than the CPU IHS, and that's why it's to simply serve as an adapter between the larger TEC and the smaller CPU to spread the heat accordingly. And then we have two connections on the side. The blue one, the tiny one, goes into the heat spreader, is measuring the temperature, and the other one is the power supply for the TEC with this small connector. And in case you were wondering what those two screws on the side were for, that's to mount the TEC controller, which will eventually sit on top like that. The controller itself is sitting inside this aluminum case. You can see also some thermal pads inside here. Going to open it in a second. Connection wise, we have three connectors. The one on the left is for power supply, the one in the center is for the TEC itself, and the one on the total right is for the temperature connection for the readout of the cooler. That's how the controller looks like inside. Yeah, by the way, I forgot to mention it also has USB connection, obviously, because you also somehow have to make a connection to your controller itself. There's an internal header right here, which is probably to flash the firmware of the controller. Otherwise, it's just a simple controller and some DC regulation. And then there is this tiny thing on top where it's reading HUM, humidity sensor, and that is absolutely great. One of the major issues back then with TEC coolers was mainly that they were stupid. The same way I made my TEC cooler, it's just a simple 2-point controller, or you just completely run it full power. Then it's very likely, let's assume you have 25 degrees Celsius water temperature and you're running full load on your TEC and your CPU is maybe sitting and idle. It's very likely that the bottom part right here could have -5 degrees Celsius, and then you could encounter condensation, which can for sure damage your hardware. And having a humidity sensor inside the controller itself can calculate with the humidity and the ambient temperature the dew point. And then, for example, you can have 20 degrees Celsius room temperature and you can run this thing at like 14 or 15 degrees Celsius without risking condensation. And that's a much smarter solution than what I had when I had the simple 2-point controller. And to improve things further, they also included this foam right here. You can see it's a little bit flexible, and the shape on the bottom is exactly the shape you have on your mainboard socket, and it should create an airtight seal between your block and your mainboard or CPU, and this way prevent condensation even further, because if you don't have like air exchanging, then you don't have additional humidity in between, then you cannot encounter more condensation. Should be quite interesting. Going to assemble everything. I'm very curious how their solution will work out. By the way, I also received this 10900K and it's a special bin. They also told me that I should tell my audience that it's a special bin 10900K, just to show what's in theory possible if you have a very good sample, because obviously if you don't have a good 10900K, then you might first want to bin your 10900Ks further before stepping up this hard in your cooling game. All right, we'll assemble everything and then see how this works out. I'm using Cryo Extreme for this application. Personally, I would prefer to use liquid metal, but in this case you can see the water block is not nickel coated, and that could be because EK made this as a prototype. I mean, this particular cooler I have on my table, it's going to be available as a product from EK water blocks, but right now the bottom of the cooler is not nickel plated, and you should avoid liquid metal with non-nickel plated surfaces, and that's why just using normal Cryo Extreme, which should also work very well. When I first talked to Intel about this project many weeks ago, then I was a little bit concerned about the backside being completely exposed to the ambient air in regards of condensation, and they said it should not be an issue, but I will just double check. That's why I mounted a temperature sensor in addition, which is touching the metal plate of the socket itself, and it's also deliberately in this area right here, far away from the VRM, which is causing additional heat on the PCB and also away from the memory sticks, and that should be pretty much the coldest area of the socket, measuring the temperature of the mainboard itself, and then we have an additional temperature sensor where we can measure the ambient temperature. Mounted the cooler, everything went pretty smooth, but I have to admit, I also didn't notice or see when Intel first showed me the draft of this PCB, I didn't notice that the USB connection was in such a terrible place. Oh well. The other two cables I think are kind of fine. The ones are going to the CPU block, I mean, the power cable and the temperature sensor cable. The only thing which is still missing is the power cable, but the rest I think looks quite neat so far. I'm already running in the 10900K, and I will show you in a second in the BIOS what exactly I set so far. Running the Maximus 12 Extreme memory is just running at 3800 with 32 GB, just enabled XMP, nothing special. Typically what you would also probably run at home. And on the bottom right in the taskbar, you can see the Intel TEC software, which is already running. And what I personally like a lot about this software is the fact that it's so minimalistic. There is nothing annoying running in the background, nothing which is stealing any kind of resources. If you check out the TEC software itself, on the top you can see cooler is running in standby mode, so it's not running right now. That's the default state when you boot up your system. You can also read power is 0 watt, which means the TEC is not pulling any kind of power right now. Dew point is calculated with just below 14 degrees Celsius, because relatively low humidity right now and about 22 degrees Celsius in my room temperature. Cooler temperature is 30 degrees Celsius without the TEC running. On mode, we can select between 3 different modes. Well, standby is basically disabled, and then we have the cryo mode, which is a regulated mode, means depending on your dew point and also the CPU load, it will run the TEC accordingly. So in idle, it's not pulling that much power, but in load, it will run according to your dew point and also your power consumption of the CPU. Unregulated mode will just always run the TEC on full throttle. Let's just try out the unregulated mode first and see what happens if we run this full throttle without any kind of safety measures. You get this pop-up message first before the TEC starts running, basically that you acknowledge that it's everything on your own risk. You accept that condensation may occur depending on the state of your insulation and also, let's say, the humidity and the temperature of your room. Gonna accept that. And then it's telling us success. After not only 2 minutes, you can already see the cooler temperature is at -5 degrees Celsius. The TEC is pulling about 160 watt. Dew point is still the same, obviously. And in hardware info, you can see all the cores in idle are sitting at 0 degrees Celsius. Well, they are running somewhere below 0 degrees Celsius, but core temp and hardware info cannot report negative values. We will do the overclocking today using Intel XTU. You can see my base settings on top. Those were applied through the BIOS. I set 1.46 volt adaptive mode, which in your eyes might sound quite a bit. And then I also left the turbo values enabled, which is 250 or 125 watt. And before some people will start crying again, those recommendations for the voltage came from Intel directly. So if you want to complain about like high voltage recommendations for overclocking, please complain to Intel, because according to the datasheet, at least if you keep the power limit in place, this should be safe for what we are doing. Now all the magic we need is called thermal velocity boost. But before we configure the thermal velocity boost, pay attention to our boost table on the left. If 10 cores are active, I push the CPU to 5.3 GHz. For example, if 8 are active, it's going to 5.4, 6 are active, going to 5.6, and if only 2 cores are active, it's boosting up to 5.8 GHz. And now the thermal velocity boost allows that you can configure those temperature values and in combination with the ratio offset on the right, which means, for example, we have the 5.8 GHz boost on one core, but then the temperature exceeds 70 degrees Celsius, and then it's reducing the ratio by -3, which means that the CPU will downclock to 5.5 GHz, and that's what you can configure with the thermal velocity boost. Intel recommendation was to try 80 degrees Celsius right here, but that was not stable for me. That's why I lowered it to 70 degrees Celsius, and this setting right here was stable for my testing. To check out the performance, we're running Cinebench R20 single-threaded performance, and it's running AVX, which means it's a little heavier than a normal single-threaded performance run. Let's say, for example, SuperPi or anything that's using SSE instead of just AVX. But on the left, you can see that basically the entire CPU is boosting to 5.6 GHz during this test. And if you run something even lighter, it can boost up to 5.8, but because Cinebench R20 is using AVX, which is fairly heavy, that means it's only going to 5.6. Let's see what the performance will look like. And the reason why we can run those frequencies is the core temperature, which you can see here. The cores without load are sitting somewhere between 10 or 15 degrees Celsius, and the single core, which has the load, is running at about 40 degrees Celsius, which is still fairly low. And you probably remember that earlier I was concerned about condensation on the backside of the mainboard, but 33 degrees Celsius on the backside, that is absolutely safe. And yeah, it's pretty warm in here, 24 degrees Celsius room temperature right now. And with this setting we can get 581 points in R20 single threaded, and that is quite a lot above stock multi-score, just above 6,000 points, not a big improvement in multi. Benchmarking and everything of course is cool, but now let's just assume that you would use this cooling solution for gaming. In that case you would like to avoid running the TEC full throttle all the time, because that means you're also consuming 160, 170 watt constantly of power, which is quite a lot. And the cryo mode, the regulated mode, is a little bit more intelligent because it keeps the block slightly above the dew point, which is typically in my region right now with, I would say, 22 degrees Celsius room temperature and a fairly low humidity, maybe like 14 degrees Celsius. And in that case, the cooler temperature can stay at 15 or 16 degrees Celsius, which is still quite cool, literally. And the TEC shouldn't consume that much power. Let's check that mode out. To enable the cryo mode, simply click on the icon and in mode select cryo. Now you can see the stats of this currently running with the dew point of just above 14 degrees Celsius, cooler temp is sticking at about 16 degrees Celsius, and the power consumption is 10 watt, which is something I can absolutely live with. That is so much better than what we had during the unregulated mode, which is something you can use for benchmarking but not constantly. While gaming, the power consumption and obviously also the CPU clock mainly depends on the CPU utilization, which then also depends on your game itself. Currently running PUBG in 1440p, and you can see on the right the CPU boost is somewhat between 5 GHz and 5.3 GHz, while the CPU temperature is sitting typically between 30 and 45 degrees Celsius right now. And in this state the TEC has a moderate power consumption of typically between 80 and 120 watt. The clock we're seeing right now of up to 5.3 GHz across all cores is typically a clock you're not able to achieve even with custom water cooling on a 10900K, except if you're running a very golden sample, then you can maybe get 5.3, otherwise you're usually more in the region of 5.1 to 5.2 GHz. One last test for fun, we're switching back in unregulated mode. I simply want to see what kind of frequency I can validate with the 10900K across all cores. For that test I'm going to switch the performance mode or the power saving mode in Windows to high performance to make sure that the CPU is not downclocking and idle, and then we will see what kind of frequency we can get with the 10-core CPU. I will also ramp up the fan speed of the radiator so we can maybe decrease the temperature by another 1 or 2 degrees Celsius. While the loop is cooling down, a quick look at the table which I was using for the gaming setup. You can see if I was utilizing 10 cores, it was running at 5.3, same for 9 and 8 active cores. Once it's only 7 or less, then it's hitting 5.4 GHz, 2 or less it's hitting 5.6 GHz. And the thermal velocity boost was set that the 2 active cores at 5.6 is only possible if the temperature is sitting below 50 degrees Celsius. Otherwise, if it's exceeding 50 degrees Celsius, it would downclock by a ratio of -3. Same for the other settings, at least 65 degrees Celsius or 70 degrees Celsius. Adjusted the power saving mode to high performance. All the cores are now synced, starting at 5.3 GHz with a sweet voltage of 1.5 volt. And the core temperature is sitting somewhere between 5 and maybe like 10 degrees Celsius, depending if there is some sudden load in the back. Alright, we already got 5.6 across all cores. 5.7 also seems to work. And we also got 5.8 GHz across all cores. Alright, 5.8 GHz was the maximum. At 5.9 GHz the system instantly crashed, but those numbers are still quite impressive considering that we're running a 10 core. Frequencies with like 6 GHz and above are usually only achievable with dry ice or liquid nitrogen cooling. That's why this is still very impressive, and it's much more than what you can get usually with custom water cooling. In this regard, I'm absolutely impressed, and this thing is something absolutely fun to play with. And that is the thing, it's fun to play with. I mean, the enthusiast in me just likes pieces of tech like this, which I can mount on different CPUs and then play around, like what kind of benchmark can I run with it, like which frequencies can I validate, can I run SuperPi 1M at X frequency and stuff like that. It's absolutely fun to play around with this thing. But my question to Intel instantly was like, is this your attempt to fire against Ryzen 5000? Like, is this the solution to catch up in like performance versus Ryzen 5000? By the way, I'm shooting this video like mid-October, end October, and this should be released mid-November, just to give you a perspective of the timeline right now. And Intel's reply was that they don't think this is a mass cooling solution, but they think of this like to show what kind of technology knowledge Intel is capable of. And I totally agree with that, because I haven't seen any kind of tech solution which is this advanced in the past. That is quite impressive. I mean, just the fact that it's calculating actively the dew point, and you have this cryo mode which is keeping your temperature at a point where you don't have condensation for sure, that is great. Haven't seen something like that before in a PC. And then it's regulated very well, which means in idle, if you're running the cryo mode, it's also very low in power consumption with like 10-15 watt, which is great. That's something much more advanced than what I was using in the past, for example. But then again, if you're running this in unregulated mode or even while gaming, it's still drawing 100 to 150 watt depending on your load. And that's something you just simply cannot neglect. And I cannot see like a million PCs using this very special cooling solution, because then like globally seen it would be a massive additional power draw, which would probably be not worth it. But that's what also Intel told me. Like, they don't see this as a mass cooling solution. It's more like what they want to show you they are capable of when it comes to technology. And the enthusiast in me absolutely likes those toys, because then can just play around with it on different CPUs. And that is also an aspect where I hope that Intel is still improving or adjusting things, because I'm sending and getting a lot of emails to them, like giving feedback. And right now I asked that they make this compatible to like all the CPUs, because currently it's limited to 10th gen CPUs. They mainly say because of the TVB, which makes sense. I mean, obviously the most you can get out of this technology is with the thermal velocity boost. But then if you're an enthusiast and you maybe want to get the maximum out of your 3770K, then you cannot use it, and that would kind of suck. That's why I hope they open it up to all the CPUs, because I don't see a reason why it should not be compatible with all the others. Obviously you cannot get as much out of it without the thermal velocity boost, but it will still be fun to play around. And that's exactly where I see this cooler, where I see this technology. It's something which is cool to play, to try around, like for benchmarks and stuff, but I don't see that like thousands of people are going to use it for gaming. But apparently that's also not Intel's idea. It has been about 2 weeks that I shot the footage which you just saw, and I've been communicating quite a lot with Intel, and they decided to also add legacy CPU support to the list, which means Kaby Lake and Coffee Lake. So for example, your 8700K, if you're still running that, you could also use it within the cryo cooler. Absolutely appreciate that they listened to the feedback. And they also made adjustments to the software, which means that it will remember what you said prior to reboot or shutdown, which means you can just reboot and it will have the cryo mode still running. That is awesome. All right, let me know in your comments down below what you think of this thing, and thanks for tuning in. See you next time. Bye bye.